Okay, welcome to the Condensed Math seminar, everybody. So it's my great pleasure to introduce our speaker today, Professor Xiao. Professor Xiao got his Bachelor of Science in Physics from Peking University in 2001, and then received a PhD in Physics from University of Texas at Austin in 2007. After 1 year of postdoc research at Oak Ridge National Lab, he became a staff research scientist there for about 2 years or so. And then he joined the faculty of the Department of Physics at Carnegie Mellon University in 2012. He recently moved from Pittsburgh to Seattle and is now a professor in the Department of Material Science and Engineering and Physics, a joint position. Professor Xiao is a renowned condensed matter theorist. He has multiple field of research in the quantum materials, including quantum electronics, and recently he pioneered the work in 2D van der Waals magnets. And Professor Xiao is a prestigious Simon Fellow, and more remarkably, he has been listed among the most cited researcher in the field of physics for several years now, I think since 2017, perhaps. And today he's going to tell us about one of his recent works on magnetic quadrupole moments in crystals and the related magnetoelectric effect. So without further ado, Dee, I'll pass you the microphone. The floor is yours.
All right, thank you. I'm taking the virtual microphone. so thanks. Do you go Shulei or Stephen in your department?
I go with both.
Yeah, so thanks for the invitation. So I remember the last time I visited the case was actually 2012. So that was, yeah, exactly 10 years ago.
Oh, yeah.
So many things happened, but the only thing I remember in the past 10 years is the COVID shutdown, nothing else. So first, I apologize for having this virtual visit, because this week I actually have to be a stay-home dad. So as you can see, by the way, if you have any questions in the middle of the talk, feel free to ask, because personally I'm very impatient. I sometimes cannot wait until the end of the talk. So feel free to interrupt. And okay, so as you can see from the title of my talk, I'm gonna mainly talk about something related to magnetic materials, and that's exactly what's gonna happen. So let me just a very interesting observation, right? Because the magnetic materials actually has been known to mankind for a very, very long time. If you go into the ancient Greek or Chinese literacy, there are written documentations about the magnetic materials. One of the examples is this materials called a lodestone, and actually the written documentation can be found starting from 6th century BC. So that was a really long time ago, and it was discovered by mankind a really long time ago, precisely because it has a magnetization. So therefore, the magnet can attract and repel each other without even touching. I think we all have that moment when we are little kids playing the magnet for the first time to witness that kind of magic. And so this kind of the existence of this magnetization is really what makes a magnet useful and interesting. And now, of course, we know that this is due to the ordering of the magnetic moment at the atomic scale, right? A very simple picture is that you can think about each of the localized moment have a spin, and they could point in arbitrary direction, but in a magnet, they would point in the same direction. So in addition to the electromagnetic applications, a very obvious application, of course, is to think about the data storage, because now all the spin is pointing in the same direction. So you can imagine, well, spin pointing up would be 0, spin pointing down would be 1. So that's sort of the basis of magnetic data storage. So then having said that, we can just play with this kind of spin texture a little bit. So let's do a very simple change, which is we're going to rotate the spin every other moment, so we can obtain this kind of alternating pattern, right? So it seems to be a very, very, very simple change, but it actually fundamentally changes the magnetic properties of the system, simply because now you have an equal number of spin up and a spin down moment. When you add them together, you get a zero magnetization. And this zero magnetization makes the antiferromagnet extremely hard to detect. And in fact, just in contrast to the history of ferromagnet, in fact, the ferromagnet, to be more precise, which was discovered 6th century BC, the existence of antiferromagnet was only established in 1930s by Louis Néel. And in fact, its direct confirmation, I think it's in the 1950 or 60, I forgot, but it's basically one of the first neutron measurement to see the doubling of the unit cell below the nil temperature. And because of that, you can regard the antiferromagnet as one of the examples of the hidden order, simply because that the magnetization is zero. But once we get used to this game of just rotating the spin and getting all kind of interesting spin texture, you can also imagine some other more complicated spin texture like this. So this spin texture exists in this compound, lithium, cobalt, phosphorus oxide. So Fibik's group has two papers recently to argue that in those compounds, you actually have those tiny vortex structure, but at atomic scale. So this is really just at the atomic scale. And now, because we are talking about this kind of vortex structure, you could have a positive or negative vorticities. So therefore, you can even have domains of this kind of vortex structure, right? So my point is that once you allow the spin to change directions, there could be more hidden order structures. So obviously, those structures are very interesting. A very famous example is high temperature superconductors. We know that its parent compound is antiferromagnet. You dope it, it becomes a superconductor. But because of the lack of finite magnetization, even in Néel's Nobel lecture in 1970, right? So the men who discovered antiferromagnet said the following thing: they are extremely interesting, but do not seem to have any applications. So it seems like we are looking at interesting but useless materials. So that sort of gave us the background of the talk where I'm going to focus today. It's basically, I want to tell you three things. One is that, okay, so now we have those hidden structures, right? How do we describe those hidden structures, at least mathematically? And then secondly, I'll try to convince you that those are truly interesting quantities, not just something we invented for a little bit of fun. And then the third is that I'm going to tell you a new phenomena that's related to this quadrupole moment, which is called an intrinsic nonlinear Hall effect. And it has a very important application in antiferromagnetic spintronics. Okay, so let's actually begin with the mathematical description of those hidden structures. As you can see that those spin textures, I mean, fundamentally, it's just the spatial variation of the magnetic moment, right? Therefore, to describe those structures, we need to encode the spin location in our description. And so let me introduce you this magnetic quadrupole, which is a rank 2 tensor Qij. So it's basically given by, I'm going to sum over all the spin in my system. And then you can see that the I is the ith component of the spin at a location n, and R is the location of the spin, and the J is the jth component. So we are dealing with a tensor here. So this is actually a very simple concept. Just as a quick sort of example, let's again go back to this vortex structure, and then we can do a little bit of calculation to see what exactly is Qij in this case. So you see that we have 1, 2, 3, 4, 4 spins. And then I'm going to assume that this square, the side of the square is A. So you can see that only the QXY and the QX tensor component are non-zero. So you can do this very simple calculation. Everybody can do it, right? So you put in all the information, you find out that the QXY would equals to negative S times A, and the QX is exactly the opposite. So in this case, this rank 2 tensor is actually anti-symmetric. So it's just a little bit of exercise to show you, how to do this type of very simple calculations. And of course, if you look at this tensor, the I and the J, so I comes from spin and the J comes from location. It's not really symmetric. So typically, what we can do is that we can decompose this rank 2 tensor into 3 parts. We can first take the trace, and then we can write it in terms of the traceless symmetric. And finally, we can have anti-symmetric, right? Any rank 2 tensor, you can do this kind of decomposition. And it turns out that those 3 different components corresponding to 3 very distinctive spin textures. So this trace part corresponding to a monopole distribution. We call it a monopole mainly because if you look at the moment, the spin direction, it as if there's a monopole at the center that is shooting out those magnetic flux. But these arrows are really just the spin orientation. And then for the traceless symmetrical one, this one is called a quadrupole. It have this kind of spin texture. And finally, for the anti-symmetrical one, is called a toroidal moment. It's like a snake eating itself, right? So those are the three different spin textures, and they can be described by the 3 component: trace, traceless, and anti-symmetric one. So even from this kind of very simple picture, you can already see that this quadrupole moment can be very useful, right? If we just want to describe the spin texture. And also the quadrupole moment has a very nice symmetry properties, is that it breaks time reversal and the spatial inversion symmetry, but it actually remains invariant under the combined time reversal and the invariant symmetry. So again, just look at one example, we can consider this toroidal moment here. You can see if I do a time reversal operation, then all the magnetic moment, of course, have the flip sign. You would obtain a vortex with the opposite vorticity. And you can also try to do an inversion. Now, if you do an inversion operation, then this spin, right? Let's choose the inversion center to be here. Then this spin will be mapped here. This one will be mapped there. But remember that a spin itself is a pseudo vector. So the spin will not flip sign. So basically, this guy goes there, this guy goes there. Then you obtain the same pattern. So therefore, those quadrupole moment breaks time reversal. It breaks inversion. And of course, if I do time reversal followed by an inversion, then I'm going to return the system to the self. So it's invariant under this combined TI symmetry. And this is a very important symmetry that we're going to keep coming back later in this talk. So finally, we can also put this theory of quadrupole moment on a more solid foundation. And to do that, we have to go back to Jackson's book, right, or any standard textbook on electromagnetism. So remember that when you consider the vector potential due to a localized charge current distribution shown here in yellow, and then the vector potential at a capital R can be written as in this form. Now, if I assume that the capital R is much larger than little r, which is where the current is located, then you can do a Taylor expansion. The zeroth order term vanishes because of the locality of the current distribution. The first order term will give you the dipole moment, and the second order term is actually the magnetic quadrupole moment. You can see it's given by this expression here. Of course, if you think R cross J as a spin, then you have this spin quadrupole moment. But by this kind of argument, we can see that there could also be orbital contribution to the quadrupole moments. Okay, so that's sort of conclude our general introduction of the magnetic quadrupole moments. Okay, but yes.
I had a quick question.
Sure.
Can we think of this magnetic quadrupole as some sort of like Fourier transform of like a spin current?
That's actually, I don't know whether you can do that, but there's definitely a relation between the spin current and the quadrupole moments. And particularly, if you think about particularly if you think about the spin transport, then in addition to, so then the quadrupole moment is S times R, right? So if you take the derivative, then you're going to obtain the spin current, or part of the spin current. You're going to have S times dr dt. But then there's also a ds dt times r, so that's like the local rotation of the spin. So I can see there's definitely a relation, but I'm not sure about the Fourier transform part.
I see. Thank you.
Right. Thanks. Yeah. And please ask me questions.
I have a question too.
Yeah.
So is it like any spin vector distribution can be decomposed into the three components, or it's only applicable for some special case of?
Okay, so basically this kind of decomposition is very general. Any rank 2 tensor can be decomposed in that. But of course, you know, in addition to the quadrupole moment, we have dipole moment, we have quadrupole moment. You can also have octupole moment. So you can keep going, and there are more information in this kind of moment distribution. So I would say that any spin texture will have the quadrupole component, but it could have even have a higher order component as well.
Okay, but that doesn't go into the decomposition.
No, it cannot be captured at the quadrupole level. You have to go to the octupole level. For instance, you can define a rank 3 tensor, say S times R times R.
I see. Thanks.
Yeah, thank you.
All right. I have more questions. Since one quick question.
Yeah.
So look at the quadrupole. This is in real space. Is there any analog in momentum space? Because the diagram you showed me just in the previous slides looks very much like the Rashba Dresser-Haus spin-up coupling.
Yeah, exactly. I think I've seen some papers, mostly from Japanese groups, talking about those spin texture in momentum space. I forgot his name, but I did cite one of these papers. I can point out later. But indeed, whether it's a real space or momentum space, to have those texture, I think the symmetry requirement is almost the same.
All right, thanks.
Thank you. All right, so those are quadrupole moments. So it seems you already think it's very interesting, but I'm gonna convince you further why it deserves our attention. So from a very fundamental aspect, this point has been emphasized by Spadin, Ferbig, and Mostovoy in this really beautiful review paper. So we can consider time reversal and inversion sort of two of the fundamental symmetries in physics, right? So if you break time reversal symmetry, then you can have magnetization, and M in this case becomes a natural order parameter. Then of course, if you break inversion symmetry, then the system could develop a ferroelectricity, and in this case, the polarization becomes the order parameter. But in the situation where you break time reversal, you break inversion, but it has combined the time reversal and inversion symmetry. In this case, it would forbid the existence of both the magnetization and the polarization. So therefore, it's not obvious that what kind of order parameter can be used to describe this kind of state. And what those people suggested is that, remember that for the quadrupole moment, right, it have exactly the same symmetry. It's time reversal odd, inversion odd, but it remains invariant under combined time reversal and inversion. So there's a strong push on, okay, whether we can use the quadrupole moment to describe those kind of state. And now, because I've been talking about symmetry for a while, and so for the people who are familiar with the magneto-electric coupling, you realize that the broken time reversal and the inversion is actually the required symmetry to have a magneto-electric coupling. And specifically, you can think about that what we're talking about here is this linear magneto-electric coupling. Means that you could have a magnetic field induce a polarization that's proportionally to each other, or vice versa. You can generate a magnetization using electric field, and from this so then this requires that the free energy has to have this form. So from here, it's very easy to see why the symmetry requirement is such, because the E field is time odd. It's time even inversion odd, but the B field is time odd, but the inversion even, right? So to allow this form in your free energy, you have to break both symmetries. And again, this is the same symmetry property observed by the magnetic quadrupoles. So it's not hard to imagine that there should be some relation. So to truly understand their relation, we can actually think about, we can go back to the literature to look at, exactly how does magnetism induce polarization. So like let's say in bismuth ferrite, there is a known multiferrics, but the coupling between ferroelectricity and magnetism is very weak. To have the strong coupling, the typical route is to have the spin texture induce the polarization. So this you can write down this expression purely based on symmetry, just to follow the spirit of the non-Dao theory. So for instance, because on the left-hand side we have a polarization, so on the right-hand side, so the magnetization should appear at least twice. Otherwise, it would break time reversal. But the P will break inversion. That's why you also need a gradient there to break the inversion symmetry. And also, you can write down a corresponding discretized version of this formula, which is given by this very famous paper, which is a spin current origin of the magneto-electric coupling from Lagausa and Balaski. What they showed is that in general, if you have a Si and Sj, and then the P would be proportional to Eij cross Si cross Sj, where Eij is the vector connecting I and J. Okay, so let's actually apply this formula to different spin textures and see how that will give us the magneto-electric coupling. So first, let's consider a spin texture that's have this monopole distribution. So the black arrows are the spin texture. Okay. So now, if you use this formula, you can convince yourself that when you have two spins pointing this way and that way, then it will give you a polarization in this direction indicated by this white arrow. Now you can do the same calculation for all the spins, and you will obtain this kind of polarization pattern. Of course, when you add all of them together, you have a vanishing polarization because the system has a combined TI symmetry. Okay. So now if you apply the magnetic field, so you can imagine that because the moments are basically localized, and so what you can do is that you are gonna tilt this moment a little bit. Okay, so then if you do the tilting, you're gonna have a larger P pointing up and a smaller P pointing down. Again, once you do this, you sum over all this, you're gonna have a net polarization pointing up. So in this case, we have a polarization that's proportional to the magnetic field. So this coefficient would be a trace term. Now, if we go to the other example, which is a toroidal spin texture, right? So now you can see spin form this vortex structure. So using the same formula here, then that's the initial configuration of the polarization. Again, you apply a magnetic field, you're gonna tilt the moment a little bit, and in this case, you are going to have a polarization that's going to be perpendicular to the spin texture. So in this case, we're gonna have this relation that P equals to alpha cross H. So in this case, alpha is really anti-symmetric rank 2 tensor. Again, that is consistent with the spin textures. So from here, you can already see that indeed, if you have this spin texture, it generally indicates that there should be a magneto-electric coupling at the linear order. So to make this kind of relation into a more quantitative form, we can begin with some simple derivations. I know that in general, I shouldn't put too much equations into a talk, but those are really simple arguments. So let's go through these arguments, right? So first, you see that if you have so N is all the spin in the system. So if you have a spin that couple to the magnetic field through the Zeeman coupling, and then the magnetic field is varying in space. So therefore, you can do a Taylor expansion to obtain the first term, which is a Zeeman coupling. But the second term, you can see that you have this S times R term, which is a quadrupole moment that couples to the spatial variation of the magnetic field. Okay, all right. So now suppose that we have this magnetic field. Then let's calculate what is the induced charge density. Because we are looking at a insulator, what you can do is that, okay, so the charge density would be proportional to the divergence of the polarization. But in this case, my polarization is actually induced by the magnetic field through this magneto-electric effect. So you do the calculation, you obtain that the induced charge density equals to alpha ij times the spatial variation of the B field. But on the other hand, right, so we can also look at this problem from a free energy point of view. And in this case, the free energy, the relevant part is those two terms. The first is, as we argued earlier, you have a Qij, which is a quadrupole moment, coupled to the spatial variation of B field. You also have this charge density, or couples to the chemical potential. So therefore, via this Maxwell relation, you can see that the derivative of Qij with respect to the chemical potential should equals to alpha ij, which is the magneto-electric coupling coefficient. So this is actually a exact quantitative relation between those two quantities. So with those in mind, this tells you that if you want to know not only whether the system can support a magneto-electric effect, but rather exactly which tensor components are allowed, which are not allowed. You can just simply calculate the Qij, and then you should know that what component of alpha ij is non-zero. So let me give you one example, which is happened in this two-dimensional van der Waals magnet. So the example I'm going to tell you about is this chromium triiodide. So I'm going to talk about a little bit about the materials. So chromium triiodide is a two-dimensional magnet. So here is the crystal structure. Those white spheres are the chromium atom, and the purple ones are the iodine. If you look at it from the side, you have basically one layer of chromium sandwiched between the two layers of iodine. So that's called a one molar layer of chromium triiodide. So back in 2017, Xiao Xu's group have shown that this is even at molar layers, you can still have a long-range magnetic order due to the very strong anisotropy. But what's interesting about this system is that if you look at the bilayer chromium triiodide, it becomes antiferromagnet. Mainly between the layers, the spins are antiferromagnetically aligned. Then once you have this kind of spin configuration, you can then calculate this quadrupole moment, right? Just using this formula here. But in this case, we can see that the QZZ term is actually non-zero. Say if you begin with here, so here I have spin up at a positive Z, here I have spin down at a negative Z. So if you calculate the QZZ, it will give you a non-zero quadrupole moment. But a non-zero QZZ then implies that the alpha ZZ should be non-zero. So therefore, it's very easy to see that not only I can have a linear magneto-electric effect in the system, but I can simply do that by applying a perpendicular electric field. Then I should induce a perpendicular magnetization. And in fact, you should see this kind of oscillation between even and odd layers. So for the odd layers, QZZ would be 0, and for the even layers, QZZ will be non-zero. So this is exactly what they see in the experiments. So in the experiment, they basically build this, fabricate this kind of device. So you have a bilayer chromium triiodide with HBN, and sandwich them, because chromium triiodide will die immediately if you in air. So anyway, you can see that this is the gate voltage. This is applied gate voltage, and this is measured MOC, which is basically can be regarded as proportional to the magnetization. So you can see this beautiful linear dependence. And not only that, if I switch the top and the bottom spin, so I have spin up on the top, spin down in the bottom. But if I go to the opposite configuration, you can see the slope will change. So this is also easily understood because when you switch between those two spin configurations, the quadrupole moment, the QZZ will flip sign, which then will give you which also will flip sign of the magneto-electric coupling coefficient. Okay. So so basically you can see that even at a very cartoon level, right, you can use the quadrupole moment as a very simple way to figure out what kind of magneto-electric coupling is allowed. And in fact, we only talk about the QZZ component, but you know, once you know precisely where spin is located in the material, you can do the calculation. You can figure out all the other non-zero components. So this tells you that I mean obviously if you are familiar with the magnetic point group, you don't have to do this, right? You can just figure out what's the magnetic point group, and then look at any tables which will tell you that which component are allowed or not. But this tells you another, to me, a much intuitive and easier way to know the magneto-electric coupling in the system. Okay, so so basically, I hope that by now I have convinced you that the quadrupole moment is indeed a very, very useful concept. It can serve as autoparameter for a large class of condensed matter systems, and it also has a very deep connection to magneto-electric effect. So having said that, the problem is that we actually don't know how to calculate this quantity. So let me see. Okay, so I'm gonna go through the next part a little bit quicker, mainly because it's a very dry part. Just talk about the calculations, but maybe I can first convince you that what's the problem here, right? So it seems like, oh, you know, it's very easy to calculate. You tell me where the spins are, I can then plug them into the formula and do the calculation. The problem is that the classical definition that I showed you earlier is actually based on the localized current distribution. However, when you think about crystals, so we're going to have an array of those kind of periodic structure. And in that case, how to do the calculation is actually not so obvious. So the reason is the following, is that if you really think about a definition like this, then this is not really a bulk quantity. So what do I mean by a bulk quantity? Is that if it's truly a bulk quantity, then if you change the surface property a little bit, in a thermodynamic limit, a truly bulk quantity shouldn't depend on the surface conditions, right? But you can see that if you follow this definition, and let's consider sort of a cylinder with two boundaries. And if I can change the surface magnetization, which is very easy to do, you can imagine that putting some atoms on the surface, or you can change the surface condition a little bit. You can change the surface magnetization. If you do that, then you plug in this thing, you plug this change into the definition, and even in a thermodynamic limit, it means that when V goes to infinity, this change will survive in a thermodynamic limit. So this tells you that if you use this classical definition to do the calculation, you are not going to obtain a truly bulk quantity. Okay, and it turns out that this is not a unique challenge for quadrupole moment. Even for the dipole moments, we already have this problem. And fundamentally, the problem is due to the position operator is ill-defined for the Bloch functions. Because you see that in the quadrupole moment definition, or in the even dipole moment definition, we need to calculate the expectation value of the position R. But if you think about a Bloch functions, it's basically a plane wave modulated by a periodic function. So therefore, the the position of the block function is actually you define. So this is already a problem in the calculation of polarization and orbital magnetization, and so how do we deal with this problem? And so the strategy we use is I already mentioned that in my earlier slide, which is that, if you cannot use the current or spin distribution to do the calculation, what you can do is actually to use the free energy, right? Because we can begin with the free energy. We have a spin independent part, we have the Zeeman part, we have the quadrupole part. And then therefore you can define the quadrupole moment as a response of the free energy to the spatial variation of the magnetic field. So once you can define any quantity, right, in terms of a response, then as theorists, we have standard ways to do the calculation. So let me quickly just flash those equations. So first is that if we only consider the spin part, what you need to do is to couple the system to a spatially varying Zeeman field. You do the calculation, you're going to obtain this formula here, which is actually very similar to the formula for the orbital magnetization. And this formula, what I want to emphasize is that it's gauge invariant and it can be generalized to the multiband case easily. And by the way, Steven, so Jonathan is the guy I mentioned that had a paper earlier talking about momentum space spin textures. Okay, so then the spin part is actually easy to calculate. What's sort of non-trivial is the orbital part. So the reason is that if you want to calculate the orbital part, you really have to worry about the coupling between the system with a vector potential, right? So in that case, it's not the B field enter into your Hamiltonian, it's the vector potential enter into the Hamiltonian. And because we need to calculate up to the order of the spatial variation of the magnetic field, which means that it's second order in the spatial derivative of the A field. So it's difficult, but not impossible. And I have to give the credit to my former postdoc, Yang Gao, who is now a professor at USTC. So we obtained this formula. There's not much I can tell you except that it's a very long formula. But one thing I did want to emphasize is that once we have that, if you do a derivative with respect to the chemical potential, it will give you the exact expression of the orbital magneto-electric polarizability that previously obtained by Vanderbilt and Joe Moore. So I just want, because this relation, as we emphasized earlier, is a thermodynamic relation. So it's really nice to see that our microscopic calculation can yield this relation. Okay, that's it. The only thing I want to tell you is that now we have the formula that we can calculate those quantities. So then the question is that, okay, but what can we measure, right? so we have this very nasty looking formulas. What can we measure? And particularly, what about mechanical systems? That's something that I'm very interested. So what I'm going to argue is that once you have those quadrupole moments, it should support a nonlinear Hall current. Okay, so I'm not going to tell you exactly what the derivation is, but I just walk you through to argue why, if I have a quadrupole moment, then I should expect this nonlinear Hall current. Okay, so to do that, let me bring you back to the Maxwell equation in matter. So the difference between Maxwell equation in vacuum and in matter is that in addition to the E field and the B field, we also have to introduce the D field and H field. And those, so to do that, we first divide the charge and the current into a free and the bound part, right? And then you can introduce the polarization and the magnetization. And remember that then the divergence of P should give you the density, and the curl of M should give you the magnetization current. Once you have those relations, then this Maxwell equation becomes complete. But do you remember exactly how did we obtain those equations? Like, how do you establish the relation between between P's and M and rho and J. And this was done via the so-called coarse graining procedure. So this is a screenshot I grabbed from Jackson's book. So remember essentially that what we have to do is to connect the microscopic charge and current distribution at atomic scale, right, to the macroscopic scale. And what you do is to introduce this testing function. This is a coarse graining process. You average over at the microscopic scale, and eventually for the charge density. So in Jackson's book 6.92, he actually said, okay, look, in addition to the polarization, because this if you look at this is basically another Taylor expansion. So you can have a higher order terms. So in addition to the polarization, the electric quadrupole also contribute to the charge density. But very interestingly is that in Jackson's book, he even said the third and the higher terms are present in principle, but are almost invariably negligible. And the entire talk is focused on those negligible terms. So if you do the same thing, I mean, in Jackson's book, he talked about the charge density, but if you do the same thing for the current density, you're going to obtain the following equation for the current. So the total current in the system will contain the free current. This is the very familiar magnetization current. Now, if you go to the next order, it will also give you a quadrupole moment current. Okay, so now the argument is the following. Now, imagine that if the spatial inhomogeneity is induced by a chemical potential gradient. Okay, so then you can see that the gradient of the chemical potential is essentially the electric field according to the Einstein relation. So the first term is corresponding to the Hall current. So it's because it's perpendicular to the E field and it's dm, and then the coefficient will be dm d mu. And the second term, now because I have two spatial gradients, that one will give me another current that's also perpendicular to E because of this cross product. But I have another E field. So this one will give me a nonlinear Hall current. Okay. So that's the basic argument. So if you want to look at the actual expression, I should go to this paper. But the point I'm trying to make here is that if the system allows a quadrupole moment, then in a metallic system, it should allow a nonlinear Hall effect. And very importantly is that this Hall effect will be intrinsic, that it will be independent of the relaxation time, because everything here is written in terms of the equilibrium quantities. Okay, so let me give you another explicit example of this nonlinear Hall effect. Oh, so I'm gonna ignore that. So let me give you an example, which is this material, copper manganese arsenide. Okay, so this material is actually antiferromagnet. So this is a crystal structure, and you can see that in the unit cell, the manganese atom can be separated into two groups. So the spin pointing this way or that way. So if you look at it from the top, then the new vector can actually almost freely rotate in plane because there's a very little anisotropy. Okay, and after analyzing this symmetry of this compound, it have the exact symmetry we want. It breaks time reversal, it breaks inversion, but it has a combined TI symmetry. Okay, and in fact, nonlinear transport has already been carried out in these systems by Junworth group, and they argue that the nonlinear coefficient should depend on the orientation of the nil vector based on symmetry, but there's no microscopic theory yet. So here we have done a calculation to study those compounds. So this is done by my postdoc, Chong Wang. So here is the nonlinear Hall effect. Again, this is a sort of a experimental setup, right? So you apply an E field, and then here you can measure the current or voltage, and you should have a signal that's proportional to E squared. And you can see that first, let me show you, this is the chemical potential dependence of the nonlinear Hall coefficient. So it has, you can see some very sharp peak structure. And I'm gonna come back to this later. And more importantly, this is the angular dependence of the nonlinear Hall coefficient. How to read this? So along the radial direction is the chemical potential. So you can change your chemical potential. And along this polar direction is the orientation of the nil vector. And a very useful feature is that you see that when the nil vector is pointing to the right versus the nil vector pointing to the right, to the left, the nonlinear Hall coefficient flip sign. This tells you that if the nil vector flip sign, by measuring the nonlinear Hall effect, I can know that. Okay, so then let's actually go back to this peak, because this is really a very sharp, large peak. So why do I have a peak here? So the reason is that if you go to the band structure of a copper manganese arsenide, you notice that around the Fermi energy, there are many avoid anti-crossing points. And typically when you have those anti-crossing points, it indicates that there will be a very large barrier curvature. So those are the barrier curvature hotspot. And it's those anti-crossing points that will give you a very large signal. You can see that this is the calculation from very simple KP model. And we can also reproduce this very large sharp, very large peaks in the nonlinear Hall coefficient. Okay. And finally, so the nonlinear Hall connectivity has become a really hot topic recently. So I just want to give you a quick rundown of various contributions and their similarities and difference. Okay, so the nonlinear Hall connectivity is defined in this way, and so far there are 3 known mechanisms, and there could be even more. So first is the intrinsic nonlinear Hall connectivity. That's the connectivity we are talking about in this talk. It's proportional. It's independent of tau, and tau is the relaxation time, and it's actually time reversal odd. Then there's another nonlinear Hall connectivity is called a barrier curvature dipole, which was proposed by Liang Fu several years ago. But that one is actually time reversal even, and it's proportional to the relaxation time tau. So for the barrier curvature dipole contribution, even in a non-magnetic system, right? If you break inversion symmetry, you should be able to measure that. But it's time reversal even. And finally, there's also a Joule contribution. And this one is proportional to tau squared. And it's actually time reversal odd. Okay. So if you want to measure the reversal of the nil vector, only the time odd part can do this job. Because for time even, so basically the barrier curvature dipole contribution will not change sign because it's time even. And not only that, if you have the combined time reversal and the inversion symmetry, it will forbid the barrier curvature dipoles. So this one doesn't even exist if you have that combined TI symmetry. And the second point I want to make is that in moderately conducting samples, okay, then the intrinsic one, because it's independent of tau, it should be the dominating contribution. And in fact, we have done a calculation. Our estimation is that in this particular materials, the intrinsic contribution is about 10 times larger than the Joule contribution, which is proportional to tau squared. Now, of course, if you go to a clean sample, then tau can become very large. And in that case, those extrinsic contributions should dominate. And another interesting direction here is that you can also think about whether you could have a skew scattering and a side jump contribution at the second order. I don't see any reason why they shouldn't, but I think that still some work needs to be done. Okay.
Sorry.
So having said, yes.
Sorry. So the nonlinear Hall effect in the copper manganese arsenide, that's not a very curvature dipole effect. That's like a Fubini metric effect.
It's not a barrier curvature dipole contribution.
So it's from the metric tensor. It's not from the barrier curvature tensor.
Right. Yeah. And because it also have a combined TI symmetry in this material, the barocode dipole is actually 0 after you integrate over the Zhang.
Yeah, but in that case, I mean, the quantum metric, shouldn't it also have this longitudinal nonlinear response in principle?
Yes, yeah. You can have longitudinal one, but okay. So what I forgot to say is that yes, of course you should have the longitudinal one, right? But in the longitudinal direction, you already have a component linear in E field, so that could probably gonna dominate the signal. But here, because you have the combined TI symmetry, the linear Hall effect is not even allowed. So any Hall current Hall effect begin with the second order effect. Okay. All right. Yeah. Thanks for this question. This is actually very important because the combined TI symmetry forbid linear Hall effect. Okay. So having said all that, so let me just circle back to the picture that I mentioned at the very beginning of my talk, right? So one of the attractive things about a ferromagnet is, of course, you have a finite magnetization. Then you can do data storage using spin up and spin down. But what I just showed you is that so if you have this quadrupole moment in the antiferromagnet, then you could also have a spin state 0 and 1 when you look at the reversal of the nil vector. I mean, typically when you think about the reversal of a nil vector, most people think that those two states are indistinguishable from each other, but that's not true. Those two states will give you opposite nonlinear Hall signal. So that's at least the read part if you want to do a antiferromagnetic data storage device. Okay, but then of course the impression that in this the impression that normally you cannot distinguish the nil vector and its reversed state is also without a reason. That's because when you look at the magnetic space group, if sometimes you have the symmetry element, let's say time reversal plus translation, then if you go to the magnetic point group, it becomes time reversal. Then that will forbid any Hall effect, right? So to sort of facilitate this material search, we have listed this symmetry table for this intrinsic nonlinear Hall effect, the Jude contribution and the Barry curvature contribution, and so you can look at this table and figure out, which material should have this intrinsic nonlinear Hall effect, and those should be the material that one can focus on this nonlinear Hall effect. All right. So having said that, let me just quickly put the summary here, and I have 5 minutes left for questions. Thank you very much.
Thank you for the nice talk. Any questions from the audience? Xiao.
And thanks for the talk. And so my question is, for the toroidal distribution, the spin distribution, why the polarization, the induced polarization is not overall toroidal too? Is in the slides it was radiant? Why is that?
You mean which one?
Yeah, it's pretty earlier.
Here, right?
Yeah.
Okay, so what was the question?
So if the illustration on the right, when the spin vectors are going in circles, why the polarization vectors are still radiant? So like
I mean, I guess the simple answer is that if you follow this definition here, right? Or the other way to think about it is that because this P is proportional to EIJ cross SI cross SJ, so therefore you can see those two spin configure like those two spins and these two spins, you can obtain them by a continuous rotation. You can rotate the spin this way and that way, but for overall spin, rotation Si cross Sj doesn't change sign because it's going to be in the outer plane direction.
Okay.
Right. So these two will give you, it will actually give you the same cross product.
Oh, I see.
Yeah, but I mean, this is just a intuitive picture to show the connection between spin texture and the magneto-electric effect, and more, if you want to have a more quantitative relation, then this tells you that you can just do the calculation of the quadrupole moments, and then the non-zero component of the Q will tell you that the corresponding moment component of alpha should be non-zero.
I see.
Yeah.
Also, I just got a quick question. In order to get the nonlinear detectable nonlinear Hall effect, do you require something like a higher voltage induced voltage range to get it work?
I think it really depends on the actual value of the nonlinear Hall coefficient. And I'm not too worried about whether you need to have a large E field. I think, okay, I'm not experimentalist, obviously, but I think you're probably gonna do a frequency dependent calculation. You have a low frequency E field at F, then you can measure the signal at 2F. And also the other reason, and also thanks for the question. I should have one slide. We actually compared our calculated value with the experiment. There is actually a magnitude of 10. So 10 times difference, like they calculate the intrinsic Hall effect, we calculate is much larger. And part of the reason is because even in the experiment they have mentioned, there's a lot of antiferromagnetic domains. So you have some cancellation in the sample. And the other thing is that this signal, you can see, is very sensitive to the chemical potential, right? So it's also very sensitive to the temperature. So I think to really pin down the origin of the nonlinear Hall effect, just to have better samples, eliminate the antiferromagnetic domain would be very, very important.
Thanks.
Thank you.
Next one, Jesse.
Hi, thanks. So if I understood correctly, you were saying that, the quadrupole moment couples to gradient of magnetic field, which then you can in turn show how that couples to electric fields, or implies a couple to electric fields. Is there any measurable effect though, just from like gradients of applied magnetic field in practice?
Oh yeah. I mean, if you apply a gradient of the magnetic field, I think you should have a charge density variation, right? I mean, because if you apply a B field, you get a polarization, which is a charge times R. So now you move R to your to your magnetic field part. So yeah, actually, this gradient of a magnetic field, of course, is what we call a spin force in the spin transport. But I never really know whether this is doable in an experimental setting, like how large a gradient you can do. So I have always thought it as a sort of a theoretical tool to understand the phenomena. But yeah, so I expect you should see an appearance of the charge density if you apply a gradient of B field.
Okay. Okay. I see two more questions. Mandela.
I already asked to maybe Walter.
Oh, okay. Walter
first.
You see me? Okay, you hear me? Hi, Dee. Nice talk.
Hey, Walter. Yeah.
I lost you a little bit though when you're talking about chemical potential variation. Are you talking about a semiconductor at that point? Because otherwise, how do you vary your chemical potential? You're talking chemical potential of the electrons, right?
Yeah. That's a really a good question. And I think when we first obtained the formula, I had the same question. So I asked David Vanderbilt, so I can tell you what his answer is. So I think because, for electron systems, you can't really distinguish the chemical potential and a electrostatic potential. So in some sense that I'm not really changing the chemical potential up and down. You can imagine I can always apply a electrostatic potential and look at the change of the system.
Right, but that works in semiconductors. So where you have a variation, you mean you have the electrochemical potential?
Yeah.
Sense, right?
Yeah.
So this would not apply to metals then.
Yes, yeah. It's not a really measurable quantity. So that's why, in fact, the reason that we went into this nonlinear whole business is because exactly what you said. Even the referee said, this is nice, but you can't measure this. But I think just as a general quantitative relation between the Q and alphas, academically it's nice. But I can also show you, this is like a toy model calculation. We have this kind of spins on a square lattice. We have the hopping in this pattern. And this is a calculated quadrupole moment. And the shaded area is the band gap. So you can see that the quadrupole moment has some non-trivial dependence inside the band. But once you go into the band gap, it becomes a linear relation.
Okay.
Yeah.
One last question, Mandela, you want to ask?
Thank you, and thanks for the nice talk. So I had a question on the slide where you were showing your former postdoc, Xiao.
Yeah. Here.
Yeah. So here, what are G and the gamma on the first line?
Okay, yeah. G is exactly the quantum metric tensor. Gamma is
that Christoffel?
Yes, yeah.
Okay. And just
right. So yeah, go.
Here, what is A and M?
Oh, A is a Barry connection, and M is the orbital magnetic moment.
Oh, okay.
So we obviously has an expert here.
No, I've just seen the G and gamma together everywhere in a geometric context. So I was just...
Right. Yeah. So So this is a part I didn't got a chance to go into, and particularly if you go to a two-band model, it's I think no, this is not a two-band model. So anyway, in this paper by Chong, did I give a reference? Anyway, it was published PL last year. We discussed in a two-band model, everything can be written in terms of geometric quantities, whether it's a Barry curvature or the quantum metric tensor.
Okay. Thank you.
Thanks.
Very good. So if there is no further questions, let's thank our speaker again. And we can stop the recording. Okay, and continue informal discussion.